Hello everyone, welcome to CSEN 503, Introduction to Communication Networks. This is Dr. Amr Al-Mogi. In the last lecture, we discussed a very important topic, which is the protocol stack. We discussed what is the meaning of a protocol stack and what are the functions of the different protocol layers. And we discussed different addressing schemes that we find in the different layers. For the remainder of this course, what we will be doing is we're going to take each layer, open it up, and look at some of the protocols inside. In each layer, there are many different protocols. They have different uses and different functionalities. So obviously, we will not cover every single protocol that is available in all the layers in this course, but we will study some of the most important ones. Starting with actually this lecture, we will actually take what is called the top-down approach, where we start from the application layer and we discuss the protocols in that layer, and then following that would be the transport layer, the data link layer, the transport layer, network layer, and then the data link layer. And so before we actually start with anything about the application layer, let us take a little bit of time to discuss what is actually happening in the internet in terms of applications. When we discuss the application layer, we are actually discussing the data that we generate, the data that we consume, what we actually want at the end of the day from the internet, our usage basically. And this slide here shows a statistic that is done every year, which is basically what happens in an internet minute. And the figure that you see here is the statistic of 2019. As you see, in 1 minute over the internet, you have about 4.5 million videos viewed on YouTube. You have 8.1 million texts sent on WhatsApp, over 690,000 hours of videos watched on Netflix. And there are many other statistics, many other applications, web applications that basically generate significant amount of data. So you can imagine that the amount of data that travels over the internet at any given time is huge. Okay, just actually by looking at this figure. If you look at the trend as what are the types of applications that are actually exchanged or that are used, you will find that there is a trend where mobile applications and video applications are of increasing demand. Okay. This trend has started around 2010, 2011, and is continuing to grow. This figure here shows only up to 2016, but the fact is the amount of video traffic and the amount of mobile traffic continue to grow every year. If you have ever wondered how much data is sent over the internet in a period of time, as of 2018, or actually I think of 2017, we went into the zettabyte era. The zettabyte is 10 to the power 21, I think. And so that's the total amount of traffic that moves around the internet in 1 year. And as of 2020, we are now reaching over 220 exabytes per month. That's times 10 to the power 18. This is a huge increase, a huge growth of traffic in the last period of time. And this is thanks to the growth of streaming platforms, as well as Internet of Things applications and non-PC applications as well. So now we can actually start discussing our application layer. We discussed a little bit about the application layer before. We said that, first of all, we don't have applications running around in the core. If we divide the internet into core and edge, we have discussed that all the applications run on the edge. The core doesn't actually run applications because it doesn't need to. In the core, we find switches and routers, and they're only interested in reading the addresses such that they can deliver the packets. They don't need to run applications because they don't read the data. And so we find all our applications at the edge. And so when you write a program, when you write an internet application, you want to write it such that it runs on the edge, such that edge devices can actually understand it, and you don't need to worry about what the network core will do with it. And we have also discussed that there are two main application architectures. There is client server and there is peer-to-peer. And if the companies have to invest actually a lot of money in establishing infrastructure, in establishing the data center that will carry the data. And these servers are always on and they have permanent IP addresses. Big companies, they have what are called server farms so that they can accommodate actually a large number of requests at any given time. This is what a server rack looks like. So data centers are made up of units of what you see here. This closet-like structure has actually many places where you can install servers. And a server looks something like that. Okay. So you install the server, you install actually a number of them, and at the top of the server rack, there will be a switch. So all of these servers will actually be connected to the switch. Now, when data comes to a server, it will arrive at the switch, and the switch will actually deliver it to a server. When the server wants to reply, it will send the reply to the switch, and the switch will send the reply along its way. Most probably, the switch will then be connected to another switch, and then another switch until is then connected to a router, which is connected to the internet. Okay. So this here is what a switch looks like. As you see in the back of the switch, you have what are called ports. This is where you plug in your Ethernet cables to connect the servers. And this here is what a router typically looks like. It's a little bit bigger. It has a smaller number of ports than the switch because it connects a smaller number of devices, but this is what you have that can actually communicate with the internet. This is what a switch rack looks like. There is probably here a screen so that if you want to manage the servers directly, so an IT person, for example, would go and use the screen and keyboard at the server rack to configure the servers or the switch, for example. This here shows you what a server farm looks like. So you see those things here. This is actually a single switch rack. This is the one that you saw in this figure. Okay, and as you see, a server farm will contain maybe hundreds or maybe even thousands of switch racks. So you can see that the server farm contains actually a very large number of servers capable of handling a very large number of requests. Okay, this in the figure here, I think it's a Google server farm somewhere in Europe, if I remember correctly. The other application architecture is the peer-to-peer, and we said an example of that is BitTorrent. In peer-to-peer, the clients can actually talk with each other directly without going to a server first. Typically, there is a server that just stores the IP addresses of the peers so that if someone wants to communicate with someone else, they can go to the server and obtain the IP address. And there are also applications that are hybrid. For example, Skype has part where you have text chatting. This is a client server because you can actually send the text message and the recipient would be offline and they will obtain the message when they become online. So that message would have been stored in a server while the client is offline. So this part of the application is client server. When you want to establish a video call over Skype or over Zoom or whatever, you go to the Skype server and you ask for the IP address of the client and you obtain the IP address and then establish a connection directly between you and the recipient. And so this connection will be peer-to-peer. Okay, so when you design an application layer program, basically you're using a protocol such that the application running in one machine will talk with the application running on another machine. They will actually be talking to each other using a protocol. They will be communicating using a protocol. So more accurately, we can say that there is a process running at an application in the first machine, talking with another process running at an application at a different machine. For example, when you open your browser and you open a new tab and you download a page on that tab, the tab is a process. Okay, and this tab is communicating with a similar process at the server. It's actually the server will actually be able to handle several requests simultaneously from different clients. And so your tab at your browser will be communicating with a process at the server to obtain the content from the server. Okay. Now, as an application developer, what do you need to worry about in terms of networking protocols? Fortunately, you don't need a previous lecture. If you remembered our discussion, we had a similar example where you had a building, and the building on the top floor you had employees, and the employees write letters and send them to the secretary in the lower floor. As far as the employees are concerned, they do not need to know how the secretary actually does his or her job. They do not need to know how the postal office will do their job to deliver the letter. They do not actually need to know anything else about the network other than the fact that they need to just give this letter to the secretary. Your application is the same. Your application doesn't need to know anything about how the transport layer does its job, or the network layer, or the data link layer, or the physical layer. The application only needs to know how it is going to give its data to the transport layer. And then the transport layer does its tasks and then gives the packet to the network layer, which does its tasks and gives it to the data link layer, and so on. Okay, so how does the application layer give its data to the transport layer? The answer is they need an interface between them, and the interface is called a socket, also called an API, or application programming interface. That's something that you probably have heard before. The socket, or the API, is nothing but an interface between the application layer and the transport layer. What is the purpose of this interface? It provides separation between the layers, so that as an application developer, you don't need to worry about what the transport layer is doing. So you can imagine the socket as a door. On one side of the door, you have your application, and you are in full control over what the application does because you design it. You actually determine what the application does and how it works. On the other side of the door, you have actually the transport layer, and you are not in control of anything in the transport layer. Maybe just actually set a few parameters in the transport layer, but you are not in control over how the transport layer does its job. This is actually because you want to keep the layers separated. If you were in control over what the transport layer does, then you would be responsible as an application developer over the transport layer as well. And you don't want that. You don't want that responsibility. You just want to worry about your application. So the socket, or the API, what you do is when you have data, you open the door, you push the data to the transport layer, and then you close the door back. When you have data, you push the data through the socket will actually deliver it to the transport layer, and then the transport layer can take over and do its job. At the receiving side, the data will go to the transport layer, and before it gives it to the application layer, it also passes it through the socket, and the socket delivers it to the application layer. So the socket, or the API, is an interface between the transport layer and the application layer. Okay, so as an application layer developer, if you don't have control over what the transport layer does, how can you then guarantee some quality over the application? Obviously, your application is dependent on what the network is doing, is dependent on how the transport layer will do its work, on how the network layer will do its work, on how the data link layer will do its work. So if you have no control over what all of these layers are doing, how can you then guarantee quality? The answer is you have actually limited control. For example, as an application layer developer, even though you have no control over what the transport layer is doing, you have the choice of which transport layer protocol to use. You can actually specify which socket you want to use. Do you want to use the socket for protocol number 1, or you want to use the socket for protocol number 2? For example, in the internet, as we will discuss in a little bit, there are mainly two transport layer protocols, which are called TCP and UDP. As an application layer developer, you have the choice of whether to use TCP or UDP. You have the choice whether to use a TCP socket, which will push your data to the TCP protocol, or a UDP socket, which will push your data to the UDP protocol. Okay. So as an application developer, when you are making this choice, how would you actually make the choice? How would you decide on a suitable transport layer protocol to transport your data? The answer to this question lies in the application requirements. What do you want your application to do? What do you care about in your application? For example, do you care about data loss? Can you tolerate certain amount of loss? For example, in real-time applications such as audio or video, you can tolerate probably up to 5 or 10% of packet loss. That means 5 or 10% of your data can be lost, and the recipient will not notice. The human eye or the human ear will not notice this degradation, this slight degradation in quality. In other applications, you cannot actually tolerate data loss at all. You have to have 100% reliable delivery. That's true of emails and web applications, for example. You can never receive an email that has errors. You might send an email and you don't receive it at all, but you would never actually receive it with errors. Another service could be timing or delay. you might actually want the data that your application generates to be delivered before a deadline. Okay. Another service is throughput. Okay, you might actually require a minimum bandwidth, a minimum amount of resources in terms of bits per second to be supported by your network if you are actually sending data. This is true of, for example, streaming applications, of video conference applications, where you are actually sending and receiving a large amount of data. And finally, one type of service that your application may require is security. If you're sending sensitive data, you may require services such as encryption and a check on data integrity. That means that no one actually changes the data or manipulates it from source to destination. This table here shows what some applications may require in terms of some of these services. For example, a file transfer application will typically require no data loss. That means the file cannot actually be delivered with errors. It probably will have no strict requirements on throughput and delay. That means it can tolerate small throughput and it can tolerate longer delays. When we say it can tolerate longer delays and small throughput, what we mean is the application will not fail. You will still actually be able to transfer the file and the recipient will still get the file. The service might not be excellent, the quality might not be excellent because, for example, it's taking too long to transfer the file, but at the end of the day, you receive the file and so the application performs well. This is in contrast, for example, with a real-time audio-video application, which is loss tolerant. That means it can lose some data, but it requires strict guarantees on throughput and delay. And because it requires strict guarantees, we can understand that if the delay is too long, the application will not be usable. You cannot actually have a voice call, and it takes forever for you to hear the person you are talking to. Okay, this means that this application will not work unless there are strict guarantees. And we know that the internet is a best effort network that cannot actually give you any guarantees, which is why sometimes these applications work well and other times they fail. And the table shows other similar examples. For example, email and web documents also do not tolerate any data loss, but they can tolerate a low throughput and high delay. And all real-time applications will require, are probably loss tolerant, but will require guarantees on throughput and delay. Whenever you have video, you're typically talking about high throughput. Could be up to 5-10 megabits per second. Okay. If it's audio only, then it's typically small throughput, but also small delay. Okay, so these are some of the services that any application may require. And these requirements will play a role into which transport layer protocol you will choose as an application developer. This is actually our discussion. You are designing an application and you want to choose what kind of socket you will use such that you give your data to the right transport layer protocol. And so these requirements will probably play a role. This is what would come to mind when you are choosing a transport layer protocol. So what do we actually have in the internet? As we said, we have two main protocols at the transport layer. We have the Transmission Control Protocol, or TCP, and we have the User Datagram Protocol, or UDP. They provide different services. TCP is a connection-oriented protocol. That means before you send data or receive data with TCP, you have to establish a connection between client and server. Okay, that means the connection has to be set up between client and server. And this is something that we briefly saw in a previous lecture, and we will go over it again in this lecture. TCP also provides a service that is called reliable transfer. That means it provides some kind of reliability for the data that is sent between client and server. Okay. How can TCP do that if the internet itself provides you no guarantee that your data will be delivered? For example, if you're sending data and you have a router, it cannot do that. What it can tell you is, once your packet is delivered, I will give you some feedback. And TCP does that. It provides something called an acknowledgement, that once the receiver receives the packet, it sends feedback that this packet has been delivered. And so what do you think TCP would do if a packet is not delivered? It will simply retransmit. And this is actually the reliable transport feature that TCP has. With this feature, You can lose a packet forever. So for example, you send an email and the email never arrives, but you would never actually receive a packet that is not properly ordered, wrong sequence, for example, or it has errors. There are other features that TCP also supports that are called flow control and congestion control. Flow control makes sure that a fast client doesn't overwhelm a slow server, or a fast sender doesn't overwhelm a slow receiver. And congestion control is a service actually for the network. It makes sure that a client doesn't send too many packets when the network is congested. Reliable transport, flow control, and congestion control, they all are services that may be of importance to the application, but they also cause delays. They restrict the data rate that you're sending with, and they provide overhead. And so sometimes they cause additional delays for the application. TCP doesn't provide any guarantees on delays or throughput or security. We know that there is, for example, HTTPS. And so if you're using HTTPS, you'll be using TCP. And on top of it, you're using something called TLS, Transport Layer Security. This is the one that provides security, and this is the Transport Layer Protocol that we're discussing. So this is TCP. In contrast, you have another protocol that is called UDP. UDP is the complete opposite of TCP. It provides very, very limited services. It is not connection oriented, meaning that you don't have to establish a connection to send the UDP packet. If you have something, you just send it. It doesn't provide reliable transport. So that means if a packet is lost, there's no way to actually detect. Does not provide any guarantees on delay or throughput or security. Does not provide flow control and congestion control. Quite often, we call UDP the blank slate protocol. And so the question arises, why do we even have a protocol like UDP? If TCP is the full protocol that has all these features and all these services, why don't all the applications just use it? Why even have UDP in the first place? There are actually many reasons. First of all, if you don't want to suffer the delays that are caused by the TCP services, then you can just use UDP. Typically, this is what happens with real-time applications. They use UDP so that they don't have to worry about the delays that are imposed by the TCP services. But there is also another important reason. Let's say you like a certain service. For example, you like reliable transport. Your application requires reliable transport, but you don't like the way TCP does it. As we said, because the layers are separated, an application developer will not have control over the transport layer protocol. That means as an application developer, you have no right to change how TCP works. Meaning that if you're choosing TCP, you have to make peace with the fact that TCP does reliable transport in a certain way, does flow control in a certain way, and does congestion control in a certain way. You cannot actually change the way TCP does that, because TCP is a standardized protocol. Anyone is using TCP is expecting to see these features work in a certain way. And so no one is allowed to change them. So what happens if you like, for example, reliable transport or flow control or congestion control, but you don't like the way TCP does them? What you can do is you use UDP as a blank slate protocol, and then you implement your features on top of UDP as an application layer feature. That means you can actually implement the reliable transport at the application layer. If you're using UDP, you can actually implement reliable transport at the application layer itself if you don't like the way TCP does it. Okay. And if we go back to some of our applications, now we can see what some of these applications typically use as the underlying transport protocol. For example, email and the web and file transfer typically all use TCP. Anything that requires a reliable delivery, they will use TCP. And here we have the application layer protocols like HTTP, FTP. FTP is the file transfer layer protocol. Anything that is real-time will typically use UDP. An application like YouTube uses actually a mixture of both, because YouTube at the end of the day is a web page. So because it's a web page, it uses HTTP, and HTTP uses TCP as the transport layer protocol. However, when you play a video on YouTube, a different protocol is invoked. It's typically called the real-time protocol, and this one can actually use UDP. So some applications, they can actually use a mixture of TCP and UDP for different purposes. And we have discussed in the previous lecture that the applications can actually address each other using what are called port numbers. The devices actually address each other using IP addresses, but in order to identify a specific process within a device, you need to use port numbers, and this is something we will discuss in details in the transport layer. Now we are ready to see the details of our first application layer protocol, which is HTTP. So we can expect in our discussion that we will cover some of the points that you see in the slide. Any application layer protocol will have to define what are the types of messages that are exchanged. For example, in HTTP, we have a request message and a response message. What are the syntax of these messages? What are the semantics of these messages? What are the meaning of the information in the different fields? What are the rules for when the messages are sent and how they can be processed? And whether these protocols are public domain, meaning that they are open for anyone to read them, or whether they are proprietary and they are kept secret from the public, such as the protocols of Skype, for example. Okay. So HTTP is a protocol. It's a very simple protocol. That's why it's so popular. It's a very simple protocol used to download resources from a server. So it's usually based on client-server communication. And so it is used to download some resources from the destination. Okay. These resources can be anything. These resources can be images, can be videos, can be text, can be anything. Okay. We use them in the web. We use HTTP in the web so that we download a web page. And to understand how this works, we have to first investigate or examine what a web page consists of. A web page, such as the one you see in the slide, consists of objects. These objects can be HTML files, can be images, can be videos, and they are all arranged together in a certain way. The way the page is arranged is specified into what is called the base HTML file. And in the project, you will actually use HTML to develop your website. Okay. The base HTML file will contain references to the objects in the web page. That means if there are 10 images, for example, in the web page, they will be referenced in the base HTML file. How are they referenced? Each object is referenced by a URL. The URL has two parts. Part of the URL specifies the host name. This is actually the name of the server where all the content is located. And the second part is the path name to that object. It's as if you are actually trying to find a file in a server on your computer. The path will contain partly the name of the folder and then the name of the file itself. Okay? So each object in your web page will have a complete URL. If all the objects are stored in the same server, then they are all going to have the same host name, but they will have different path names. Okay? So what you do when you want to download a web page, the first URL that you send to the server is the URL of the HTML file, meaning that you will request from the server first the HTML file. You will receive the HTML file and then you will parse it. And when you parse the HTML file, you will find actually the references to all the other objects. You will find the URLs to all the other objects. And then you go and request each object independently using its URL, and then the server sends them to you. And once you receive all the objects, or as you are receiving objects, your browser actually compiles them and shows you the web page that you are requesting. Okay. This is basically the process that HTTP facilitates. It's the request of objects from a destination. HTTP is very popular because it has only two simple types of messages, and they actually do all are the request messages and the response messages. The request messages are typically initiated by a client, and they include the URL of the object that you are trying to download. The response will actually contain the object that was specified in the URL in the request. Okay. So you see here, you have a server running a web application, and it's receiving requests from several devices. and it is sending a response back containing the objects that are requested. HTTP is ultimately a stateless protocol, meaning that it doesn't remember what the client requested. For example, if the client sends 10 HTTP requests with the same object, HTTP will not remember that these objects were sent. Okay, it will actually treat every request independently. There is a technique that is actually used to allow servers to remember these objects, but this is something we'll discuss later in this lecture. Now, because HTTP requires reliable data transport, you never actually download a web page that has errors. You might actually not have a good connection and you will not be able to download the web page at all, but you would never actually download it with errors. And because of that, HTTP uses TCP as the transport layer protocol. And because of that, that means before you can send the TCP request, you will have to establish a TCP connection between client and server first. So if you have, this is the client and this is the server, first you send a TCP request, you receive a TCP response, then you send an HTTP request and you receive an HTTP response. Okay, this is roughly the process of HTTP. Now, how does the HTTP protocol handle the TCP requests with the server? Over the years, there has been several versions of HTTP. The newest one now is called HTTP 3, and it's used by all the major providers like Facebook and Amazon and Google and all of these providers. We will not actually discuss these advanced versions of HTTP in this course. We will discuss actually the earlier ones so that you can get an idea about how HTTP was developed. Now, initially, the way HTTP managed TCP connections is that you have to have an independent TCP connection per object. That means when you want to download an object, you open a TCP connection, you send a TCP connection request, you receive a TCP connection response, you send an HTTP connection request, you send an HTTP request, and you receive an object in the HTTP response. And after that, the connection is terminated. The TCP connection is terminated. Okay, this is in HTTP 1.0. This caused significant delays because if you have 10 objects to download, that means that you have to open a TCP connection for every object. It would go like that. You have TCP request, TCP response, HTTP request, HTTP response, and then the connection is closed. If you want to download another object, you have to send TCP request, TCP response, HTTP request, HTTP response. Okay, you have to keep doing that for every object. So if you have 10 objects, okay, you would have to have 10 TCP requests, 10 TCP connections. Starting HTTP 1.1, they use something called persistent HTTP. This is called non-persistent. Non-persistent means that the connection does not persist. The connection is closed after every object. In persistent HTTP, you can actually download multiple objects with the same connection. That means if you have 10 objects you want to download, first you open the TCP connection, you send the TCP connection request and receive a response. Then you send one HTTP request, okay, you receive a response. You send another HTTP request, you receive a response, and you keep doing that until you download all the objects, and then when you're done, you terminate the connection. So in persistent HTTP, you have to terminate the connection yourself. The connection is not terminated automatically after one object. With persistent HTTP, servers now had to have something like a timer, that if the TCP connection remains idle for a long period of time, the server can actually automatically terminate the connection without going back to the client. This is so that because the server will have a limited capacity on how many TCP connections it can keep open for simultaneously, it must actually make room for other connections that are not idle in this case. This slide here shows an illustration of how non-persistent HTTP would work. So first the client initiates a TCP connection. to the server and then sends the TCP connection request. The server will receive it and send a TCP response saying that it accepts the connection. Then the client sends an HTTP request, including the URL of the object that it wants to download, and it sends this HTTP request through the TCP socket. Okay? If you remember the discussion of the sockets earlier in the lecture, the sockets are what are used to push the data from the application layer to the transport layer. Once the server receives the request, it generates a response message that includes the object that is requested and sends it back to the client. Once the client receives the object, receives the HTTP response, it parses it, finds the object, and then closes the connection. Okay. How do we measure the performance of HTTP? We talked before about delays, and we said that delay is a very important metric to actually measure performance. However, typically, if you have a client and a server, typically what you will see is that you will have many routers between the client and the server. So if you want to measure the delay, we are always referring to the end-to-end delay. That means the delay from generating a message, sending it to the server across the routers, and receiving the response back. So we use a metric that summarizes all of the delays between client and server, all of the queuing delays, all of the processing delays, all of the propagation delays, and this metric or this term is called the round trip time. And we define the round trip time as the time for a small packet to travel from client to server and back. Time for a small packet to travel from client to server and back. Why do we say small packet? Because round trip time includes all the delay components except for one delay component, which is the transmission delay at the server. So all the components of the delay are there. All the queuing, all the processing delays, all the propagation delays, and all the transmission delays as well, except for the transmission delay of the final destination or the server when it sends the response back. So such a small packet is, for example, the TCP connection request and response. So the round trip time would be the time taken for the TCP connection request to travel from the client all the way to the server and for the response to come back. This total time is called the round trip time. Now, in non-persistent HTTP, you open first a TCP connection, as you see in this figure, and then you send an HTTP request and receive a response. So how much time does this take in terms of RTT, the round trip time? You see here that we need 2 round trip times to get the response back, one for opening the TCP connection and another one for sending and receiving the HTTP request response. But as we said, the RTT doesn't actually include the transmission time at the server, and so we added to this delay. So the total delay is 2 round trip times plus the transmission time of the object from the server. We don't include the transmission time of the TCP connection response because it's a small packet. So we assume it's already included in the definition of RTT. Okay, that means if you have non-persistent HTTP and you have 10 objects, how many round trip times would it need? It would need actually 20. You would need 10 round trip times for establishing TCP connections and another 10 round trip times for the HTTP request and response. So in short, you would have actually 2n round trip times plus the summation of the delays, the transmission delays for each one of the objects. This is the total delay that you see with non-persistent HTTP. With persistent HTTP, you open the connection only once. So this is 1 round trip time for opening the connection. And then you have 1 round trip time per object. Every object needs an HTTP request and then a response. You only have 1 TCP connection in this case. So you have n plus 1 round trip times plus the summation of the transmission delays for each object. So as the value of n grows, you can see that the savings in delay in persistent HTTP becomes significantly higher than in non-persistent HTTP. Okay. And now we can actually take a look at the, before we proceed, there is actually something that also saves the delay in persistent HTTP. And by the way, persistent HTTP was used starting HTTP 1.1. There is something else that you will see in the tutorials, which is called pipeline. Basically, what we have been saying so far is that you open a TCP connection request and receive a response. You send a request and you receive a response. You send an HTTP request and receive a response, and so on. Now, what is happening is that you have one RTT for the TCP connection request response, and then you have one RTT per object. With pipelining, what you do is, first you open the TCP connection, so TCP and TCP. And then what you do is that in a single round trip time, if this is one round trip time, you can actually send multiple requests, meaning that you send multiple requests without actually waiting for the response. And the server, once it receives these requests, it will actually send the response back. So with pipelining, you actually need just one round trip time to send all the requests for the objects. And so it will be 2 round trip times plus the summations of all the delays. So pipelining is an additional feature in HTTP 1.1 that saves a significant amount of delay also in retrieving the objects. Now we can actually take a look at the structure of the HTTP request and response messages. This here shows you the request message, and it starts with something called the request line, which starts with a command. The command is what the client wants the server to do. There are specific commands. For example, the one in the slide shows you the command get. It's the one that is mostly used. Get means that you want the server to give you something. What do you want the server to give you? This object that is specified here. And then you specify the version of HTTP. After the request line, you have a bunch of header lines. The header lines provide additional information about the request. For example, here the first header line is the host. That's the name of the server. And the host name plus the path in the first line or the request line consists or make up the full URL of the object. After that, the other header lines are optional. For example, here you have the user agent. This is the type of browser that you're using. And you include the type of browser because sometimes the server has different versions of the web page for different types of browsers. If you have ever downloaded something on, for example, Internet Explorer, and it looks different from how you see it on Chrome, because the server will actually have different versions of the web page, and it will give you the version that is most suitable to your browser if it has one. If it doesn't have one, then it will just give you the default. Or if it doesn't support the browser that you are using, then it will just give you the default one. Another header line says accept language. This is also a useful feature. It tells you, I want the web page in a certain language. So for example, here we want the web page to be in French. If the server has a version of the web page in French, it will give it to you. If not, it will give you just actually a version in English. If you have ever tried to actually access the websites of some of our partner German universities, you will see that the website is usually in German, and there is a button that says English at some place on the web page. If you click on that, you will be sending an HTTP request to the server with accept language English, meaning that you want the web page in English. And there is a very important header line here that says connection close, meaning that I want the TCP connection to be closed after this object. This is an important addition in HTTP 1.1 or persistent HTTP because the connection will not be closed automatically. You have to specify when you want the connection to be closed. Okay. This is the generic format of the HTTP request. You start with the request line that has a method, get, for example, and then the URL and the version, and then a bunch of header fields, and then some terms that you want to supply to the server. For example, if you want to search for something on the server, you can enter your search terms in your entity body. You have different methods. It's not just get. You have different actually methods that you can use. You have post, for example, if you want to upload something to the server. If you want to upload a full object, you use put. Okay, so put and post are similar. It depends on if you're uploading an entire object or you're just uploading, for example, a few terms. Okay, There is also delete if you want to delete an object from the server. And there is something called head. Head is for debugging. It means if you are sending actually an HTTP request that says head instead of get, the server will respond to you with an empty response, indicating that it actually can respond, but it's just something to for debugging. Okay. In HTTP 1.0, the earlier version, only these three methods were supported: get, post, and head. And this here shows you the structure of the response. It starts with the status line, and the status line tells you what happened with your request. Here you have the version, and you have 200 OK. 200 OK is actually the desired response. It means that the request has been processed successfully, and the response includes the object. There are a bunch of status codes that indicate different meanings. For example, 404 not found. That's something we are very familiar with. It means that the server did not actually find your object. 400 bad request. It means that the message was not understood by the server. There was a syntax issue. 301 moved permanently. It means that the object is no longer there. And 505 version not supported, meaning that you are using actually a different HTTP version than the server is expecting. Okay. After the status line, you also have then a bunch of header lines. For example, here the server is saying connection close, meaning that the server is confirming that it's going to close the TCP connection after this object. And then you have date. This is actually the date when the response was created. You have also the type of server. This is the same as the type of browser in the request message. Here the server is telling you what kind of server is generating this response. Last modified is the date when the object was last modified on the server. And then you have the length in bytes and the type of content, whether it's text or an image or whatever. And then you have the object itself. Okay. So these two things show you actually the structure of the request and the response messages. Last thing we will discuss in this lecture is an additional feature to HTTP that converts it from stateless to stateful. We said that HTTP is a stateless protocol, meaning that if you send 10 HTTP requests with the same object to the server, you will receive actually 10 responses, and the server will not know that all of these requests are actually coming from the same user or the same client. The system of cookies allows the server to remember the user. Okay? It allows the server to store some information about the user, and it's a very useful feature to many web applications. For example, some marketing applications, they like to save what you are actually doing, what you are searching for, what are your habits. And so they want to remember what kind of HTTP requests are you sending. And so, and with these HTTP requests, they know exactly what kind of objects you are looking at. Okay. The cookie system has 4 components. First of all, there is an additional header line in the HTTP request that includes your cookie ID. And there is an additional header line in the response indicating what is your cookie ID. This is the one that we provide, that the server provides to you. And this cookie ID is kept in a special file in the browser of the user that is called the cookie file. And by the way, every period of time, your computer will prompt you to delete the cookie file or delete the history. And in this case, all the cookie IDs will be deleted, and you will be contacting each server again as a new user. The server will not recognize you. It means the server will have to build back your history. And at the server, there is a database that saves also the cookie IDs along with all the data that the server is interested in, such as your usage patterns, for example. Okay. This figure here shows you how this all works. So if you are actually using the cookie system, and let's say this is the client, and the client has a browser, and the browser contains only one entry in the cookie file, it says eBay 8734. That means that this is the cookie ID that was provided to the user or to the client by eBay. Now let's say the client is contacting Amazon, not eBay. And it's the first time ever the client has contacted Amazon. So the client will send a usual HTTP request message, no cookie ID or anything. The Amazon server will receive this request and will recognize that the client is new. That means it doesn't have actually any cookie ID. The request is not containing any cookie ID. So when the server generates the response, it will include a new header line with the cookie ID. It says set cookie 1678. It means the server is providing the user with a new cookie ID. When the client receives this response, it will save this new entry in its cookie file. Okay. Now, the next time the client accesses the server, it will include the cookie ID in the request, and then the server will just generate a response message that is a function of this cookie ID. That means it will take the cookie ID into consideration. Okay. If 1 week later you want to access the same server, you again will send the cookie ID in the message. Now, this has many advantages as that it allows the server to save some information about you and allows you to allows the server to provide you with a more customized service. But it is very important to say that this comes also with many privacy issues. That means the server has saved a lot of information about you that you may not actually want the server to save. And so in all or almost all modern applications, they tell you beforehand now that they are using cookies, and it's up to you whether to accept or deny that the server will save actually information about you. That's it for this lecture. We'll continue this discussion next time.